Okay, this is part 2 of Introduction to Vectors. The next topic is, how do we state a vector quantity? Suppose we want to tell your best friend you've got a force vector and you want to tell them or show them what exactly is the magnitude and direction of that force. There's 3 ways. The first way is you're simply going to get out a piece of paper. You're going to maybe put a frame of reference. I suppose you could do it without a frame of reference, but I'm going to use a frame of reference. You can see for a 2D frame of reference, we've got a y-axis going up and down the page and an x-axis going across, so that's by convention. And then I'm going to draw an arrow on the page to represent a certain force. But before I do that, for this to be legitimate, I need, oh, that's bold. I need a scale. So my scale is going to be 1 centimeter on the paper. I'm just, whatever's reasonable, equals, and of course it depends. If you've got a huge force, you're going to want to make your centimeter equal to like 100 newtons. I don't have a huge force in mind, so I'm going to make mine like 5 newtons, which is a little over a pound. Then what I'm going to do is I would probably have to get out a protractor to get the right angle, but since I'm just kind of making this up, I'm just going to draw an arrow. Remember, it's an arrow, and I'm going to say, hey, this is my force. And actually, this fully describes this force vector quantity, because this drawing, this sketch, this arrow completely describes the direction of the force relative to your frame of reference, and it is the magnitude. So if you handed this to your friend, and what would they do to really, okay, well, what is the force really? Well, first thing they would do is they would go down to the scale and they'd say, okay, I'm going to have to get a ruler, and they would take the ruler and then they would measure it, and I'm just going to pretend that this is 4 centimeters long. I'm not worried about sig figs here. Okay, so what is the magnitude of the force vector? The force vector is, it would be, so force vector is 20 newtons, and then we need to have a way of direction. So your friend would have to get out a protractor. It's a little bit of a hassle. And they would measure, okay, you could measure any angle, but we're going to say by convention. You're going to hear that a lot, meaning people before us just decided this would be a good way to do it. So by convention, we typically measure from either the positive x-axis. This, of course, is positive x, so we would measure from that. Or suppose that you had a vector that was pointing over here. Just call this F2. Then we'll see, and this is just introduction. We're going to be doing this in detail later. Then you might measure from the negative x-axis. So your friend is going to take out her protractor and she's going to measure, and that looks like 1, 2, 3, 4, 5. Okay, it's not going to be quite 45. So let's say we're going to say 40 degrees. I lost my black. Oh well, we're going to be doing blue here. 40 degrees. 40 degrees. And so to fully describe this vector quantity, I'm going to go get my black marker back. Okay, I found my marker. So we would say then is, okay, then it's 40 degrees. The orientation is 40 degrees. And you know which 40 degrees? And so we have to be a little bit more specific. So we're going to say above the positive x-axis. We will be doing this later in more detail. Okay, so it turns out that the directed line segment does fully describe a vector quantity. It's a little bit of a hassle. You got to have a ruler in your pocket. You got to have a protractor in your pocket to translate it, but that's what it is. And what's nice is by explaining why a directed line segment works to communicate a vector quantity, we have essentially just described the second way. So let's just summarize what we just did. So the other way, a second way that you can fully describe a vector quantity, is you just simply state it as a magnitude With force, it would be something in newtons. With displacement, it would be something in centimeters or meters. With velocity, it would be probably something in meters per second. As a magnitude and a direction, you could think of it as polar coordinates if you've done any work with that. Otherwise, just think about it. Hey, a vector has a magnitude and direction, and if I can simply state the size of this vector quantity and its direction relative to some frame of reference, which I have, that's magnitude and direction. So that's this guy right here. The last way to communicate a vector quantity is to state it as the sum of its components. So we're going to say this is going to be the component method. Now this way may seem kind of strange, but when we start adding vectors, which we will do a little bit with velocity vectors and a lot with force vectors, when we start having to add vectors, turns out you can't just add them like numbers because they have a direction. Then the component method is by far the most precise, probably the fastest, the easiest way to add vectors quantities together. So now you see I have a frame of reference. I've got my x-axis running across the page. I've got my y-axis of my frame of reference going up and down. And you'll see that there are two vector representations. Basically, we're going to say vector A and vector B. Technically, they're not the vectors themselves, but they are those directed line segments that represent vectors. Okay, that probably was too much. It's just say there's vector A and vector B. And we want to use this thing called the component method to describe vectors A and B. So the first thing I'm going to do is think about a box, dashed line box that encloses vector A with one side of the box is parallel to the x-axis of our frame of reference and the other side of the box is parallel to the y-axis of our frame of reference. I'm going to do the same thing for vector B. And what we do with the component method is there's this word called resolve. It just means break down the vector into its x component and its y component. So you can basically, that's another way of saying we're going to essentially break these vectors down to their x parts and their y parts. And the boxes are going to help us do that. So let's look at vector A. You can see that vector A doesn't go in the x dimension, and it isn't in the y dimension, but we can kind of think of it as consisting of an x part and a y part. And the way we're going to say, okay, the x part, we're going to write it as the same letter A with a subscript x, and we're going to keep that little vector hat on. And then on the y-axis, we're going to call that A subscript y. And it turns out that vector A can consist of, basically can represent it as the sum of these two components. So we'll say vector A can be described by consisting of the x component of A, vector A, plus the y component of vector A. And the gizmo is going to take you through this process, but let's do a sample here. Now, to come up with quantities, I'm going to have a scale. So we're going to say that one block, and I guess these are going to be force vectors. In the gizmo, they don't worry about units. They're just math vectors with no physical meaning. But one block is going to be equal to, let's make it 10 newtons of force. Let's just do it. Okay. So this is our scale. This goes back to our previous way of representing as direct line 70. But for us to come up with numbers in the current, where we are right now, we need to have that scale. So how long are these two vectors that are the components of vector A? So I am saying vector A is 1, 2, 3, 4, 5 blocks long. Because what we're going to do is we're going to actually put a number in here for A. So basically 5 times 10 is 50 newtons. And then we're going to go over and we're going to do the same thing for the Y component. I see it's 2 blocks tall. So 2 times 10 newtons per block is 20 newtons. Okay, now we have to communicate to the world, well, which one of these is for the X and which is for the Y. And so we're going to take these. I'm going to stay with blue, I guess. I ended up with blue. So we're going to put these weird little vector hats. And the way I want you to just think about it, and the way I'm going to say it is, so this would be 50 newtons in the X dimension. And this one would be 20 newtons in the Y dimension. So that's what this tells us. This is in the X dimension, and this tells us it's in the Y dimension. I may have gotten that backwards. X dimension, Y dimension. All right, that's going to seem abstract, and that's going to seem, well, why would you bother doing that? Well, when we get to adding vectors, you're going to see the beauty of the component method, because this is how we're going to add vectors. Let's do B real quick. So vector B, we're going to break it down. I'm going to do black now. So vector B, we're going to break it down into its X component vector plus its Y component vector. And so I can see that it's 2 blocks wide. That's the X. So I'm going to say 10 newtons. But notice which way the vector is pointing. The vector is pointing, the X component is pointing in the negative X direction. So we need to put a negative sign there. That's how we capture the direction, the negative direction. Okay, so that's going to be parentheses, and then there's this weird X with the caret hat. You can call it X hat. But I say it's negative 10 newtons in the X dimension plus, and then we have to figure out how much is in the Y dimension. 1, 2, 3, 4 long. 4 times 10. Wait a second, I made a mistake here. Using the wrong scale. Each scale is 10. Sorry, let me go back and change that to 20. Sorry, I've been using a different scale today. So that's 10 newtons per block, negative 20. And then BY is 4 blocks down. And so that's going to be 40. But again, we see that it's pointed in the negative direction. So we need that negative sign. And then we're going to put this weird little symbol, Y hat, which just means, hey, that's 40 newtons in the negative Y direction, and that's how you represent them. Now, the beauty of breaking things into their components is really best seen if we want to add these two vectors together. I'm not going to do it, I'm just going to give you a preview. If we wanted to add these two vectors together, suppose that they were two force vectors, and we wanted to know, okay, what's the overall effect of these two forces acting together? We can't simply just add them like numbers. We have to add them. And it's so easy because now that you've broken these vectors down into their components, we're going to take the X components and add those together. And then we're going to take the Y components and add those together. And you'll see, it's a pretty straightforward process. This is the hardest part, is just thinking about breaking these vectors down, resolving them into their components. And that's enough for part 2 of this Intro to Vectors.